Hi, I want to calculate an example of what happens when there is a moving source and a reflection involved in a Doppler effect problem for sound waves. Now, in general, with the Doppler effect for sound waves, we get a shifted frequency that's equal to the original frequency times the speed of sound plus or minus the speed of the observer divided by the speed of sound minus or plus the speed of the source. And the top sign is for relative motion towards, the bottom sign is for relative motion away. And I have a burglar alarm that's sending out a constant 28 kilohertz frequency pulse. It's stationary. There's a burglar that's moving away from that alarm at a speed of 0.95 meters per second. And let's say that the alarm happens to be in a continuous broadcast mode, constantly sending out that sound information. Well, whenever you send out sound, where it hits could be considered an observer. So bouncing off the burglar is an observer of that sound wave. But the echo, the reflection that we get, is reflected at the frequency that the object that it reflects off of would hear. So if that alarm that's stationary bounced off a stationary wall, it would bounce off at exactly the same frequency. But because that initial observer is moving, there would be a shifted frequency detected by the observer, which would then reflect off that shifted frequency, and by having a moving source, that would introduce an additional shift in the frequency. So all reflections involving relative motion have two components to the shift in frequency that we see with the Doppler effect. So, in the first instance, our source is stationary and our observer is moving. But since the burglar's moving away from the source, I'd use the bottom sign in my numerator, so the frequency that the burglar would detect would be the original frequency broadcast by that alarm times the speed of sound minus the speed of the burglar, which the speed of sound in air is 343 meters per second. So it would give me 342.05 meters per second divided by, since it's stationary source, 343 meters per second. So I'd have a frequency that reflects off the burglar of 27,922.4 hertz. Now, the alarm would hear a doubly shifted frequency. So that frequency would be the frequency that reflects off the burglar. Again, we would use the same parameters, however, this time the observer is stationary and the source is what's moving. And the source is moving away from the observer. So since the relative motion's away, we use the bottom sign, so that means we would have the speed of sound divided by the speed of sound plus the speed of the burglar. So our doubly shifted frequency would be our shifted frequency of 27,922 hertz times 343 meters per second divided by 343.95 meters per second, which would give me a frequency observed by the alarm of 27,845.3 hertz. Now, you might think it to be a little ridiculous keeping this many digits along the way. Well, one of the neat things with waves is the process of interference. And when you have two wave sources that are playing the waves that are of similar frequencies but not quite exactly the same, the net result is a physical effect called a beat. So in the case of ultrasound, if you were to be in this scenario, continuously moving at 0.95 meters per second directly away from that alarm, then you would hear the difference in the frequency that is being produced by your reflection. There'd be a 155 hertz beat detected by that alarm. So one thing I want to point out, I very carefully called the sound because this really isn't the proper way to handle Doppler shifts when we talk about light, and radar happens to be dealing with light, which is any form of electromagnetic wave. But the whole idea of a Doppler radar is when that radar reflects off moving clouds, it shifts the frequency of light just a little bit. And by determining that shift in frequency, they can figure out the speed of the objects that are being reflected off, in addition to the density of the clouds and all the other factors that go into determining that weather forecast. Well, having that speed, and it's not just speed, they can figure out the direction too, because if there's a change in direction at a similar speed, you would get a shift in frequency as a result of that. So if you see an area where you scan and there's a rise and fall in frequency very suddenly, it would be almost like whirling a speaker around your head playing the same note. You would hear a little bit of a siren effect, and that's part of how early tornado forecasting is able to work, is that by finding those shifts up and down in frequency, they can find swirling winds, and from that say conditions are right for a tornado, and give up to 15 minutes lead time of warning, which in the event of an emergency like that is a massive amount of time for preparedness. Thanks for watching.